So are there no questions from the last time? Everything's clear. Okay, then let's start. Today we'll be looking closer on inter-process communication. So during the last lecture we had a look on synchronization and stuff like that. And what now also might be very interesting is of course how one would go about communicating between two different programs. Just need to now it shut down somewhat. Somehow the Virasio was hanging here for a short while. So let's create a new project. For convenience we can always create just a Qt console application since we don't need to use the Qt parts, but it's nice if we can use them later. So we call that pipe server. We need two programs of course to test inter-process communication. So one will be called server, the other will be called client, obviously. Zack, finish. Okay. And the second one. So under Windows there are quite a few means of inter-process communication. Most of them are rather Windows specific. So the most obvious method of inter-process communication in Windows is sending messages from one window to the other, which is somewhat convenient but also very limited. So you cannot send large amounts of data. If you want to send more than just a couple bytes, then what you will need to do is you will need to allocate some memory in a way such that the other program could access it and then just share the address, which is rather a convoluted way of doing things. Also, it's as said, a very Windows specific way, so like Linux based operating system don't allow for such means of communication. The most generic method of communication between processes is called pipes. So the idea is that you can create an object, a named object with a name that another process by this name can open, and then one end can just write into the handle as if it would be a file, some data, no matter how many, and the other one can read from the object like from a file, and everything that's sent in on one end will come out on the other end. So this is quite a convenient mechanism. So we will quickly implement it. While Qt of course provides some own wrappers to do that without understanding the underlying platform API, we will first try doing it the native Windows way, so the way you would do without Qt, and then we can do the same thing using Qt's provided classes that expose this functionality in a very user-friendly way. So we need first a variable to hold our pipe name, and we should include Windows H. This will be Unicode, and let's go with I don't know, my pipe, something like that. Then let's create that pipe. As you see, IntelliSense already suggests what values to take. Operation mode, pipe access duplex, then pipe mode. So you can operate the pipe in a few different modes. So one is where it reads like a stream of data, so you just write an arbitrary amount of bytes and you just read a stream on the other end, and the other mode is a message mode, where the blocks of data that you send in actually keep their length. So in a stream, if you put multiple blocks into the stream on the other end, you just receive a stream, so you don't know where the blocks, how the blocks were partitions when they were put into the pipe. If you are in message mode, you don't have this issue. You then know how they were partitions, which makes the communication easier, because you don't need to somehow communicate the length of each block, assuming that this is a relevant information. If you would use a highly text-based protocol where it's quite apparent from the message content when the message ends and the next starts, then of course that is not a necessary advantage, but it's nice to always use the message mode. And read mode also message. And we want also to set how many instances of the pipe we want to create. So we'll have the server and it will be able to receive connections, and if we go with unlimited, then we can have as much as we want. So as many as connect, and we'll need to have a buffer size. So let's define something for this. Size, let's say, let's go with 1 kilobyte. Buffer size and security attributes. Timeout we don't care, and security attributes we make null, since we want everything to be able to connect to the pipe. We could specify more specific security attributes here if we would want, for example, to create a pipe from a process with system privileges and allow non-system process to connect to it. But since for this example we will be doing everything as a user, then the processes will be able to communicate without the need of specially setting up any permissions. Now we check whether we managed to create the pipe. Invalid handle value. So if the return is an invalid handle value, then something went wrong. Okay, and Windows offers this getLastError function to allow you to retrieve on a per thread basis the error code that caused whatever previous operation you had here to fail. So internally, the create named pipe call is translated by the kernel32 library to a call to the NTDLL, and those calls always return a status code, and the return objects are returned by reference for one of the arguments, and this wrapper simply will translate from the NT error code to a Win32 error code, and save this with setLastError to the current thread's error variable. Okay, so we can do this, and when we return 0, good. So now we will wait for a connection. So connect named pipe. Oops, no. And then we can check whether it worked. So if it didn't work, and the thing is, this thing can sometimes return false even if it worked out. So we can check whether getLastError is equals pipe connected, and then we will just fake this and say it's true. Okay, and if this is true, so if the connection was established, then we can start reading data from our pipe. So we'll make a loop. Then we need a buffer. our buff size, then we need a variable that will hold the amount of bytes that were read. And the nice thing is that now we can use the normal read file function to read from our pipe. So pipe, then comma. We want to know how much we read, so we already had it. So this was a large R, capital R, and we don't use overlapped I/O. We could actually check whether it was successful. So we keep the return value. We test if. So if we had an error, then we'll break. At least in some cases. So if the pipe is not, so if the pipe is broken, then we want to break. If we have another error, then we want to continue and try reading again. So here, as you check if we actually read something. If this is greater 0, then we can print it to the console. Okay, and when at some point the pipe was closed, then we'll set break out of this loop. So here we'll close our pipe. Okay, so that's the most simple implementation of a pipe server. Then we will make a slightly better one, because ideally we would want to receive the connection, start using this connection in a separate thread, and then be ready to get the next connection at this from the same pipe. So like basically start listening again for the next incoming connection. So we will put this part in the whole part of the code in a loop, and we will create a separate thread to read from the pipe that we just have received the connection from. Okay, now we need to create a client. Are there any questions at this point? Or is it simple enough? So just to say it one more time, such a pipe is basically an object in the kernel which acts like a buffer and looks like a file. And by the name, it can be addressed from any process. So let's copy here our name, so we don't need to type it again. We also should use our buffer here. We will need this buffer size later. And let's connect to our pipe. So and if you want to connect to a pipe, we don't need a special function. We can use the create file function call, which we would normally also use to read and write files. We want to read and write, so can generic read, generic write, 0 here, 0 there. Okay, we want to open it, and again we don't need any further parameters here. Then we check whether it worked, so we can copy this code piece here. I failed to, just need to adjust the error message. Okay, and let's prepare some message to send. So char test 1 2 3. Write file pipe comma buffer comma then we will get the amount of bytes that were written. So at some point, if we would just be writing data to the pipe, and the server would here need very long to process the data at some point, at the point where we actually filled up the one of the buffers, the write operation would fail, indicating that the buffers are full. So then we would need to wait here until the other end has read everything, and then we could continue writing to the pipe. Okay, but for now, just want to quickly test by sending one shot message, which is much smaller than the buffer size, so this should work. Let's start it. Still compiling. Okay, so our server, wait to create pipe. Oh no, did I mistype something? Yes, I mistyped. That should be if it is invalid handle. Also, that was suspicious that error code was null, so error codes usually are not 0 but something other than 0, indicating what went wrong. Okay, so this one is running. Now we can start the other one. As soon as it starts, you'll open another window, and here it should print test123 from the other thread. Yep, well, it almost worked. We are missing here a terminating character, so we could improve on that. Buffer bytes is equal 0. This will ensure that we will nicely not print any junk to the console. Suck. And this worked perfectly. So as you see now, it is set up such that it just terminates after it had received one connection. So now we'll try to do the same thing, but in a better way, such that we can receive connections from multiple clients and don't need to terminate after one client. So let's just disable this code block and then create a new one. Then refactor the code we have here. Suck. Okay, so well, this we could move up since it's a global thingy. The name, let's leave it here. And the only thing we need to do for here is we'll create a loop where we put this in. Let me think. Yes, suck. There will be a few more changes. Okay, so we create the pipe, that's normal. Then we check whether there was an error, that stays the same. Then we do the connection, and then if we are connected, this part will be different. And of course we don't close the pipe. We would only close the pipe if the connection would, if this would fail somehow. So we just close the handle and then reopen and repeat. And here we will create a thread to receive the data. Client thread pivot param. Okay, so we will be passing. Maybe first let's do this part. So already know what will be at the top. So here we just create the thread. Okay, thread null 0 comma. Now we pass the oops. And now we pass the pipe that just got connected as the param. Why doesn't this work? Suck. And creation flag 0 and secure and thread ID we don't care, so we just pass 0. and we need to close the handle since we don't want any resource leaks. We should actually check whether that thread was created successfully, but I think that's not really likely. Let's add here a message that there is an incoming pipe connection. Okay, so we copy here our H pipe, cast our parameter. So what, as I already showed you with the threads in the last lectures, you have a free parameter which you can give into the thread, and then this parameter will be the first argument when initializing the thread in your thread function. So here we have our pipe, and then for the content here we can in principle just copy this part here, and then okay, we don't need this. Oops, brackets. So basically we have the connection, and in this thread we will just be reading in a loop, and once the connection terminates, the thread will also terminate. We also need to return some return value. We do just return 0 since we don't care for what we are returning. Okay, so let's run this quickly. Okay, and then start our client here. And now each time we start the client, we will get another message here that we received from the client. What we of course can do, we can also play a round of ping pong by sending back whatever we received. Should add here backslash. So write file pipe, comma, buffer, we use the same buffer. As size we take our byte thread, comma, the new variable for the bytes written, but of course we expect this to be the same as what was read, and we don't need this, so this is it. And now on the client end we will need to read from the pipe as well, so here we will just add read file. Actually we could just copy this part here, and if we can copy more since we are lazy, we can copy this whole code block. Did we call the buffer here differently? Our buffer is only so much, so let's create a bigger buffer just in case, and start with the capital letter, but we also just give it the size buffer size. We are not in a loop, so here we don't need the check, we just check if we read something backslash. Okay, so let's run this. That will not work because the server is down. We need to start the server first. So now whatever we sent will be automatically sent back. Zack. Nope, it doesn't. Wait, let's stop everything. Something's not completely stopped.
So both processes have to run?
Well, the server has to run first, obviously,
yeah,
because the server, and then we have to start the client. And if we start them in the right order, then it works. So we see here an incoming pipe, and we get an answer.
So if the server is terminated, the pipe is terminated as well, because you said it behaves like a file, so I thought maybe it's completely asynchronous.
Well, as soon as you close one of the two participants to the pipe connection, then the pipe will be broken, because it's only intended as a means of inter-process communication. So there is no reason of keeping communication open once one of the participants terminated. Okay, so this match to this. And what we now can do is we can do the same thing, but using Qt's Qt provided communication facilities, which is somewhat much more convenient. Well, at least slightly more convenient. We will see. So let's first edit our server to be Qt based. The most code we can save on the server side. The client side, we don't save this that much, but it's still more convenient to use Qt classes whenever possible. Okay, so to create the server, we will actually create a new class. Let's call it pipe server. Okay. It was local server. Or is it not? No. Or was it local socket? It might have been local socket. Shit, we have not added network support to this project. That's why. So while it's just local inter-process communication, the way Qt categorizes it is it's a part of networking functionality. So Qt network here. But before we add it, we should select our projects. Okay, we don't have more configurations, so in this case, it's fine. No, there should be. Okay, there is not. In the past, normally always a 32-bit configuration was also created, but apparently with the newest thing is with the newest Visual Studio, it does not do that automatically. Okay. We need a constructor for our pipe server. We will want to pass the name and the parent object in case we want to set one, and then we need to have a slot. Is that private? Private slots on connection. Then we want to have another slot on message. And we will want to be able to use this as a return parameter, but this will be for later. Let's first just install the very basic part of our pipe server. So we go here, we need the constructor and the signal, in the slot. Okay, server ist gleich Yoko local server. Did I forget? Small typo. Okay. And as it's customary for this Qt stuff, we will be connecting a signal to a slot. the server sends a new connection signal whenever a new pipe connects to it, and we want this to be connected to the current this object we created to the on connection slot. Sorry, I copied the wrong one. Wanted to copy this one. Zack. Why is it complaining? Server. Do we have too many? No, that is enough. Here we have one too many. Now it's fine. And now you of course also need to start the server. So server listen on name. Good. And now in the on connection, what we can do is we can get the local socket, which will be wrapping a connected pipe. Expanding connection. Okay. Now we will need some sort of client object on the server side to represent this incoming connection. So let's be lazy and create it in the same two files. There is no need to create always a new file for a new class. It might be elegant, but it's not necessary. Let's call it pipe client. Should define this as public as well. And we will also need for the constructor the local socket, so this thingy. Zack. Then let's create a destructor just for good measure. Actually, we should probably have created one for this as well. But for now, let's just leave it empty since we don't need it at the moment. And now this we need to include qthread. Okay. And we need a few more things, so we need some slots. So on disconnect, which will be triggered when or once the pipe terminates on the other end, and we will want to have a signal that will send a message, and this we will then connect to this slot here. So void message const string reference text und reference return value. So the idea is that we can receive something, then process it in the main thread of the pipe server, and then return a string to be sent back to the client. So this we will enable later, and then of course what we also need is our run function. Okay, let's start implementing the insights. What we will also be needing will be one more object, but that we will create later. Actually, we could copy it to the down since we don't need that, and for good measure add some commenting. Pipe server is here, then we have here our pipe client. Okay, so first thing we need is the constructor. Okay, so we have our client, that should be QThread. So we will move the client to the new thread. That first we ensure it doesn't have any parent. Why is it complaining? Okay, then we need to include local socket as well. Okay, then we will move it to the thread. Every Qt object has a thread affiliation, and that decides how the connection between signals and slot is executed. So last time we took a look on the different blocking and non-blocking methods of connecting signals and slots, and for the auto connect to work properly, the object needs to know in which thread it is supposed to exist. Okay, so we did this. Now we can connect. Oops. Pack client. Disconnected with this on disconnect. Okay, and we start the thread. We just need to still implement this and implement the run function. Okay. So in run we will just start the message loop, and in our disconnect we will just set that we want this object to be deleted on the next best occasion. Qt offers this delete later function, which is pretty useful if you want to dispose of an object, but you are still in a function within the object which first needs to finish. So if you call this, then the object will be disposed as soon as the call stack from wherever you are returns to the message loop of the current thread. Okay, and what we now also need is something to read the actual data from the client pipe. So we'll create yet another helper object, pipe reader. This will be just a normal Q object. Let's try to copy as much as we can. Zack, zack, zack. It will here name the. I will take the client. It also has a parent which will most likely remain null. And then inside we will add yet another couple of slots. Right on data red, which will be triggered whenever there is data to be copied from the buffer, and we'll also create on it a signal like here. The nice thing is that we can connect one signal to another signal and don't need like a in-between function to cache anything. Okay, so we want our pipe client to be able to access protected members, so pipe client, then local socket mpeg client, and then for the data we are receiving we need a buffer, so use a qbyte array and call it buffer. Okay, that's that much to this. Oops. Before we create all the inner parts of it, let's first finish with our finish using it. So here in the pipe server we will connect the one signal to the other signal. So since we are lazy we can copy this. Well, first we should create the object maybe. Okay, so and we need to add the object also here to our thing. So c mp reader. So we can create it here still in the main thread. We can give it already the client. We don't pass any parent parameter, and we move it also to the thread in which we are creating right now. Okay, so then we will take the reader signal. What was it? Message const co-string reference, and we connect with this, and this time we just go for as well signal. Voila. And then we started. Do we need to do anything else? Yes, there are a couple of more things we could do here. We should actually use the destructor to wait for the for the stuff that's running within the thread to terminate. So first of all we post a quit message to our event loop, and then we wait for it to finish forever. We assume that it will finish at some time, and then we want to delete mp the reader which we created. Since the event loop is terminated and the thread is terminated, it's safe to delete it from the other thread. And in run, there's one more thing to do. mp reader, mp client. We want to set the parent of the client we have to be the reader itself. We can do it here, and then we start the execution. In principle, we could also delete reader after the execution finished here. Maybe we should do that. That's nice. Okay. And now to finish the implementation of our reader, we copy the. That was not here. This. We copy our constructor. I always have this parent assignment even if I don't use it, since it's good practice to have it, and if you have it then you won't forget it wherever you might need it later. Now we need to assign this. Okie dokie. Now then we need to connect the data read signal, so at least read read this, and we called our slot on data read. We need of course to implement our slot as well. So since this message like pipe mode of operation is more a Windows thing, it's not universal on all platforms. Qt normally just operates in the stream mode, so it will not maintain block separation, but if you put in text, it will be just everything globbed together to one long piece of text. So here we will want to reassemble it. I just to add one more fix here. Here we are setting the length. We are setting the length to be set, but we would like to send also the terminating character, so we make +1. So as you might remember, C strings are always null terminated, but this null termination is implicit, so we don't need to write it. It will be always added at the end of your string. So we add here +1, and now we will be just looking for the 0 in our data stream to see when our data package is completed, since the null will not appear as like this in any text, as that means it's end. So we can append to our buffer everything that we could read. So mp client can use the read all function, which just reads everything. Now we will check whether 0 is already something that we read. So int len is equals buffer punct index of. Nice thing about Qt is that it provides a lot of very convenient functions on all its objects, like this index of and etc. So if it doesn't find it, it returns -1. So if it doesn't find it, we can return here as well. But if it found it, then we can allocate a variable for our return value. Then we will emit the message signal. The emit is like it evaluates to nothing. It's as you see here, it's just empty. But the preset syntax highlighting for Qt makes it look like a keyword, and they thought it's a good idea if you do that to make the code more readable for if a human wants to read it, so that it's clear where a signal is emitted in comparison to what would be just a normal function call. So it would work perfectly fine like this, but it just looks nicer if you use this emit. Okay, now we need to add the text. So qstring from UTF-8 mbuffer large B. From the buffer, we will just take the part that we need. So they could have been multiple messages sent. Then we add here our return. As you remember, this is passed by reference. So when the other end of the signal, where in the slot we change red, then this will be blocking until we return. So we will need to take care of this when we connect the other signals. For it to be a blocking connection. I might have not thought about that before, so we will see. Now we check if there is a return value. So if there is none, then we don't do anything. But if it's not empty, then we will use the client and write to it the return value, again UTF-8 encoded. Okay, and last but not least, why is that complaining? Sorry, there should be 2. UTF-8. Does anyone knows what UTF-8 is, or should I quickly explain it? Okay, no one says anything, so I guess you know it. So, and last but not least, we need to remove the data from the buffer which we already have consumed, and that would be it. So now let's quickly go back here to our server and create something that will consume the message which we received using our sockets, using our signals. So here Q object connect. No wait, that's not right. That should be here. Yeah, client, comma, signal, we already typed it somewhere. I'll just copy this part and edit it accordingly. So signal, message, oops. We want to connect it to this, but to a slot of the same things, and we want to use Qt blocking connection. We want a blocking connection since we want the return value to work. Okay, and then in our, have we not implemented this yet? Yes, we did not, so let's implement on message quickly. Zack. Oops. Okay, and on message we can queue debug. I think we remember this already from the last time. And we might need to include that, though it's not complaining yet, so let's see if one of the other things are included, and we'll assign return a some reply to be sent to the client. So it should be all. Let's run it. No, we forgot to start there. We need to, and there was an error. Okay, there was a semicolon missing. Is anything else missing? Compile. And that's a copy paste mistake. That should be, that should look like this. Signal, and here as well. Yeah, copying and pasting stuff is convenient and nice, but it's also error prone. Okay, and now we just need to create a server. New, it's how do you call it? Pipe server, just pipe server. And we will also need to include that somewhere. Okay, and pipe server takes as argument the name of the pipe, and you may notice that this whole prefix part here is not necessary. So on Windows all the paths start with this. So Qt decided to just ditch the prefix and just go with the name only that's necessary to establish a connection. Okay, and let's now start our client. Okay, we have here some problem. Pipe server line 21. 21. So connect client signal. Why it's complaining? Pipe server private on message text and read. No such signal. Alright, wait, on connect. I think we forgot something. Yeah, we forgot to create a client, of course. That is an embarrassing bug. So let's create this quickly. Pipe client. There's a problem if you have like more than one client object, and like one is client and the other is also client. So let's call one client and the other one my client. Is client new. Pipe client, which takes I should call this socket. That would alleviate any and since we are here in the server, and this thing will be a thread, so this will have a parent of this. Okay. Yep, now it should work. Also for consistency, let's change this to p socket everywhere. Here, okay, and here as well. Okay, reader also gets a socket. Let's run it again. Nope, we forgot one rename here. Suck. Okay, let's start client. So it wait, it's still not happy. Why? Okay, it says it doesn't like blocked Qt connection. Let's just go with Qt connection. Qt connection should not be enough, it should be blocking, in my opinion. Let's see. That's new. I mean, we could switch to the Qt5 version where this error doesn't occur, but let's stick with that and try to debug it. So they don't like the idea of just passing a string. That normally should work. Or I probably mistyped just something. No, that looks actually right. Qstring, no, that looks... Nope. Okay. I forgot the semicolon. Zack. Okay. What is it one? This is strange. That should be a registered type, and whether it's a reference or not a reference should have no effect on the connection. Okay. Don't think the problem. I think the problem is really with the that this must be blocking, because otherwise it knows that it cannot properly pass those things. But the question is, why is this not connecting? Let's try it again. But it will just now complain that there is a deadlock detected. Yeah. We probably screwed up something with the to which thread those the things belong. So we are here in the pipe server. The pipe server lives in the main thread, and then the client is the pipe client, which does not on message signal message. I mean, we could, if we leave it at auto connect, it will not complain, but then we should not be able to pass the return argument back. But we can see what it will do out of that. If this will change anything. Okay, this way it worked fine. On this end it received the message, but that should without specifying that it should be a queued connection, that probably will make trouble. Wait, I have an idea. I think I know what's the problem, because here we have the where were we? Pipe server here. Nope. There. The client as such, it lives in the same thread. So when we connect the two signals to each other here, this one will need to be blocked queued connection. Yep, that's the problem. Blocked queued connection. And now it should correctly return the return value, this thingy to here, and then send it back. Let's try it. Okay, I closed the window too quickly. Zack. Okay. And this now should contain, yep, valid text. And we got our blah back. So after some initial starting pains, it works fine. So any questions at this point? Especially about this threads and objects and connection thingy, because as you see, it can be quite confusing to a level where even if you know what you are doing, you might easily make a mistake and end up with a problem. But at least the debug messages are reasonably helpful and tell you what's wrong. No questions?
Yes, I have a question.
Okay.
So this cpipe server is now a local server on your machine?
Well, it's just a class which has called a create pipe internally. So the cpipe server does nothing different than what we do here. It starts a thread, it makes create pipe. In this internal thread, it waits for a connection, and if the connection connects, if the pipe connects, if a client connects to this pipe, then it will emit as the signal new connection, and then from this new connection we can take from this, using this next pending connection function, the pipe, and internally the thing should have emitted the signal, put the pipe on a queue, and created the next listening pipe for the next connection to get in. We can, for example, put a breakpoint here, run it again, and then we will see from where it comes, although that might be obviously we will probably not see much when I think about it. We'll just, because if this runs in a different thread, but no, it should run in the current thread. We will see where does it come from. Qt network. Okay, that's good. So here, that file we don't have. No, we will not be able to show that one. Yeah, this file we should have somewhere. Source. Okay, it found it. No, we cannot go further up. So it's actually waiting on an event, and when a connection gets created, then it will here create a new listener to the pool and emit a signal with to indicate that we have a new connection pending. But there is not much. I mean, if we go to the top and look for, then there will be somewhere like create named pipe. So here it has this create named pipe function, and I think it will be using callbacks. It will not be blocking and waiting. It will just set up everything and then wait for a event to be triggered by Windows internally that there is something happens. So let's see. We have here an event handle, so that it has had to create somewhere earlier, or it will actually wanted to receive that event. Here it's created. So when we start listening, it creates the event. It adds the event notifier, and then here when it starts, when it creates the pipe, it passes the event to this structure, which tells Windows that once the connection is established, it should trigger this event. And then using here, when we go back, using this event listener. So this is a special class in Qt which is used to interact with Windows specific parts, with Windows specific behavior. What happens is when the event triggers, then this event listener will trigger its own signal called activated, and then this will trigger the slot on new connection, which is an internal one, which then will here add a new listener. So prepare the next pipe for an incoming connection. What does it do? It removes the old listener from the list, and then it somewhere it must put them on the pending connections. So these pending connections should somewhere have a append or something like that. But it's split up into multiple files, so it's possible that this will not be in this file, but because normally there would be also a Q local server without a window. So let's copy full path and open the original file. Well, not original, but the platform independent file. So here we also have this clear has connection checks and Q. Yeah. So the incoming connection here is probably what is called. Yep, here. So when it executes this function, when we go in, we create a new local socket which gets the internal pipe handler and is added to the queue of new connections, and then the new connection event is finally emitted, from which we found it, which is then in our case connected with here. So then using the pending next, it first of course checks whether there is something in the queue, and if there is something in the queue, it will return it and remove it from this queue.
So the pipes are saved in this cpipe server.
So the cpipe server internally opens a couple of pipes with the same name, and as soon as one of them connects, then it triggers this on connection, and then the pipe can be taken out from this pool using the get next pending connection, and internally it will create a new pipe to replace the one that has now been connected with the client object.
And it will be taken out into the connected client.
Yes.
Okay.
Any more questions? Okay. If there are no more questions.
Actually,
yes?
Just one more question. So now this makes maybe not. I'm a little bit confused because of the terminology. So this can in principle be also run over a network where I have an Arduino and the classes are saved there, or am I mistaken?
So normally pipes are just local to one machine, but the method which is used here is very similar to sockets. So you can easily adapt the code to use a network socket and the TCP server instead of a local server. Qt uses a shared abstract class for the local socket. So if we go to definition, or they don't, no they don't, but it's still very similar. So a lot of operations are in this QIO device, like reading files, writing files, waiting for data to be read, etc. And we can create as a next example the same thing, but not using pipes, but using network sockets, and it will look very similar. So we could actually copy most of the code and just make minor adjustments.
So maybe you could repeat. Then if this all is local, then why do we use this pipe and server and client system in the first place?
Because it's in two different processes. So on Windows, every process can only, except to do something special, access its own memory. It cannot access the memory of another process in normal operation. Of course, you could like use specialized functions to access the memory of other processes, but this is not something that you would want to use when just two processes are supposed to communicate. So here what you are doing is you are using this pipe mechanism to define a easy to use interface between the processes, how they can send data to each other. So for example, if you have a process, some service running on your system which can do anything, control an Arduino connected to a COM port, for example, and then you would want other programs running on your system to be able to talk to the service and tell it what to do. Then you would often just use such a pipe mechanism, especially because the server that creates the pipe, the named pipe, can specify the security descriptors. So, for example, accessing COM ports usually requires you to have administrative privileges, and here you could create such a server that mediates that, and then your user mode application would not need to ask each time it starts for administrative privileges. What you of course also can do is just change the security descriptors on your COM ports to allow anyone to connect to them, but that might not necessarily be the most safe or secure thing to do. And these pipes are used in many. So, for example, different applications. For example, when you run Firefox, you will notice that there are many processes named Firefox. It's not like one process nowadays which offers the window, but usually you will have many processes. One is the main process which renders the part that you see, and then there is a couple worker process in the background which will actually render on the backend side the website that will be displayed to you. So you may, for example, have seen sometimes that that one of the tabs or a couple tabs crashed, but the whole rest is still of Firefox operational, and this happens if one of the backend processes gets terminated because of some error. And these processes often use pipes, or in case of Firefox, they not often, but they just always use pipes to communicate with the main process. And the way this works is, for example, the whole rendered page content is just sent from the worker process to the front-end display process, which then is just displayed as a bitmap. And if you click something on the website, then the front-end process will send, using a pipe, this information to the renderer worker that there was a click event that offset this and that with the following button. So there are a lot of examples like this nowadays where programs use pipes to communicate internally between some main UI component and some backend workers.
Okay, and can these pipes also be used for different programs to communicate with each other, or
Yes, that's the point. You can, as long as they know what to communicate, then any program can communicate with any other program using a pipe.
Okay, thank you.
Okay, any more questions? Okay, if there are no more questions, then let's take a short 10-minute break, and then we will continue with trying to do the same, but this time using network sockets, so that we can see how similar this method of communication really is. And if anyone has questions in the meantime, you are free to ask at any time.
I was thinking, can you hear me?
Yes? Yes, I hear you. Hello?
I cannot hear you. You are muted.
Oh. Now you can hear me.
Yeah, now I can hear. So I have a question. So I'm
Mhm.
I'm imagining this. Let's say I have an application, and let's say
Oh, I can give you a great application that you should remember. Well, not remember, but at least close to you. You know the Ultima experiment, right?
yes.
So at some point there, we have this MOPS software, which I wrote a long time ago, where you can control the whole data acquisition and lasers. And we had a source which had a plate that you could move, and the moving electronics was implemented using an Arduino. And I wrote a separate piece of software that just talked to the Arduino and had a pipe, and by sending commands over a pipe from the MOPS application to this movement manager, you could control where the source is going and what it is doing.
Okay, so you have the buttons, and the buttons were programmed to send pipe messages. And
Yes.
these messages were the commands for the
Yes.
Arduino. Okay, because I was gonna ask what sort of communication would you get? So let's say you have two windows, right?
Mm-hmm.
And they are written on different programs. So you want to different like instances, and you want to click on a button. Let's say one of them. Okay, for example, let's say one of them is a control for a laser, and the other one shows you the laser parameters right, that it gets from a certain device.
Yes.
So on the first one, let's say you want to click to. Let's say I wanted to make this sort of like a feedback thing where I click it, and I want to align my laser or like increase the intensity through an external device that is controlled through the second program.
Well,
and then the first one reads, okay, let's say you have a laser, and the second program is reading the detector to see how much power it has.
Well, it's a different level of abstraction, because what the pipe is, it is just a connection where you can send in any array of bytes, and it will come out on the other end in the same way as you put it in. So it's happening on a much lower level than where your buttons are. So what you would do here is that if you press a button, then the button would need internally, for example, if assuming we write it in Qt, you would connect a button pushed signal with some internal slot, and the slot would then do something like pipe write, and then write some text which represents what the button command is. Like, for example, set power double point 500, let's say 50%.
Yeah. Okay.
And then on the other end, just in your laser control program, which receives those commands, it would need to be, of course, written to understand those commands. So it will receive the string, and then it will say, aha, someone wants me to set the power to 50%.
All right. But then, okay. So I can see mostly the utility of this pipe would be sending commands is great.
Yes, and the programs have either to be written by you or have to provide an interface, a documented interface for you that you know what to send. So you cannot use a pipe to communicate to a program which does not expect communication through a pipe. That would just not work.
Okay, because it also, okay. And you can do that with an Arduino, right? Because you can write your own program, and then you can get your pipe in.
Well, you would have a program which on one side would open a pipe and wait for connections, and on the other side it would open a COM port and talk to the Arduino, for example. And then it could internally change, for example, the command format. So since most Arduinos have very little memory, and computing power, you might want the communication over your COM port not to be text-based, but something binary, while you would want the communication towards your program be something text-based. So you could have the service mediate and then translate the human-readable text-based commands into some binary commands which only the Arduino understands.
All right. I can see. And let me think. Okay, can you think of any use case where I would want to really send text through the different windows?
You mean text as text?
Yes.
Well, for example, if your Arduino needs a text input, then you would send text. Or if you want to, for example, what you could do is you could create a program and a server. So on Windows, you can have like one person sitting in front of the computer and another person being remotely connected to a different session, which is not displayed on a physical display locally. So you could have a backend service, and then every user on the machine from his session can connect to it, and then they could send chat messages to each other. One, the guy sitting in front of the computer, and one connected through remote desktop. And then you would want to send normal human readable text for your chat application. Or what you could also do is
thinking, I was thinking, for example, let's say I write a little application that reads my email and has like a little, all my emails, and then it can sort it into different places, for example. And I make a new window that writes a new email, right? When I click like write email, then it shows a new window and I write it, I can have just sending, not doing anything, but just sending it through the initial program.
I'm not sure what you want to achieve. Both programs would need to be set up to communicate with pipes. So we need to write some email backend and the email front end for this use case.
But let's say the first one can read your emails and can send emails, right?
Yes.
And you make this new interface that is prettier to write the emails, right?
Well, but you could also put the nicer interface directly into the other program if both are written by you.
Okay, but if for some reason I wanted to get two windows for some very specific reason, I could communicate between it through the pipes.
Yes.
Even though it wouldn't be the best maybe in this scenario.
In this scenario, I don't see why you would want to split it in two programs. So if you can do something in one process, then do it. For example, the reason why Firefox or most web browsers for what's matter now are using many worker processes is,
I noticed.
Is security, because normally if you don't care for security, you could just have one process and a lot of threads within the process. But then of course everything that any of those threads do is done with the same privileges that the whole process has. So if you have a program that runs on the desktop and shows Windows, this already means it can access the desktop object and in principle any other window running on the system at this level, at this integrity level. So if you, for example, open a text file with some super secret information and then have another program running which is a virus or a Trojan or something at the same user account on the same desktop session, then the program could just read out the text from the other window without issues. And if you create worker processes, you can set the security. So you can do two things. First of all, you can create them without any access to the desktop object, so they cannot interact with the mouse, they cannot display anything on the screen. They can only internally render an image and send it through the pipe to the display component, and the display component will check, okay, is this a valid image? It looks fine. Okay, then let's show it to the user. And if the user clicks or pastes some text from the clipboard, then it would send those text or those typed letters to the backend process. And if this backend process would be compromised, then it couldn't do anything except communicate garbage or communicate some fake data to the main process. But then of course it's the responsibility of properly designing the main process such that no matter what the worker sends to it, it will not allow for privilege escalation. And aside of course of this access to the desktop object, what you can also lock down is all the file access permissions, everything. You can create a restricted token for your worker process, which will pretty much not allow that process access to anything on the system. So even if the worker, for example, needs access to some directory, let's say a web browser will usually have some sort of cache. So it would be expedient if the workers could access the cache. But for security reasons, you would not allow them to access the cache directly. They could only send a request to the broker process that hi, I'm your worker. I would like to get this data from that cache entry, and then the broker process will validate it, and then it will only access the files from the cache. The worker wouldn't, if it's properly designed, never have the ability to say to the broker, hi, I would like to read this random file called secret.txt or things like that. So that would be just outright denied. You would probably also not allow your worker processes to have any ability to enumerate directories, because normally this is not something a program that knows what it's doing needs to do. This you need if you have like some user interface or you want to show files, select file, etc. But even if you have like a large cache, then you would not like have just a cache of named things and then enumerate a directory to see whether you have what you want. But you would know, okay, there is a database file called this or that. Then you can access this and then see how the resource would be called. So there would be no reasonable use case for a worker, for a browser worker to enumerate directory entries. Likewise with registry, for example, you could log out all the access to the Windows registry. The main problem here really is that if a program is locked down that tightly, then it is pretty much useless. It can just interact with itself and the network, if that's permitted. So you will need this broker that will show things to the user and, where appropriate, allow access to other resources.
Yeah.
What else you could do with pipes? That might not be the nicest thing to do. Yeah, some programs use some license servers. Like you have some licensing service running on your system, then you need to have the right hardware dongle connected to the system at all times, and usually then the front-end application would just use a pipe to communicate to this DRM service to check whether the token is present, instead of directly trying to access the hardware.
So pretty much anything that is in between the different, well, I was gonna say applications, but really it has to be written by the same person. Okay.
Well, you need to have you have to know what to send over the pipe. Like with a network socket, you need to know what to say to get a meaningful answer, or to get the other end of your communication to do something you want them to do. Normally, usually it's used rather for your own application. So it's not customary that someone would say, hi, this is my program, that's the pipe name, and you can send those things to it. If anything, then they would rather make a program and then provide you a DLL, which would have a defined interface, and internally it would then just use a pipe to communicate. Because you can have a really nicely documented interface with a DLL, and you don't need to pass text, etc. You just call whichever functions you want, and however it does this internally, it's then up to that DLL. What we can do, for example, here do I have this installed? I have it somewhere. I have a tool that allows you to list all the pipes on the WinMin. Okay, it didn't know the driver. And then pipe. Somewhere should be pipe. Oh no, it's called named pipe. But it's not ordered alphabetically. That is not so great. I can just type N. Okay, let's don't care for the name. Let's just go for dot pipes. Was it pipes or was it pipe? What was the original prefix? Just pipe. Okay, search. To just search all the handles for named handles that have this prefix. Sorry, It was pipe, not pipes. Then it should find them. Although that might also evaluate to device/named pipe, so I'm not sure which name. So on Windows you have a lot of aliases for different things, because when they created the Windows NT kernel, they wanted to do it more Linuxy sort of way, but then on the other hand you needed everything to be represented also with those paths and those names.
Yeah.
And hence there are a lot of these aliases. Okay, yeah, so you can use this what was it? Shorthand to access named pipes, but in the system that will actually be always located under devices named pipe. So here we have, well, it's not that many, although on this Windows there is not much installed. So this Mojo thing is that's from some browser. You can enable the process. Okay, MS Edge. The interesting thing is that most of the web browsers, whether it's Firefox or Chromium derivative, use the same sandboxing mechanism internally. But mostly we have, let's sort it by process. So this we don't care. LSA, these are some security features of Windows. So using this service you can create new users, remove users, change user permissions. And this is also, so you also communicate with that using pipes, but you would not communicate with the pipe directly. You would rather just use one of the Windows DLLs that export functions like add user, rename user, delete user, etc. And that would internally then call this pipe for you. What else do we have interesting here? So a few printer related functions. So if you want to do some printing, then your data will also go through a pipe between your application and the print spooler service on your system. A lot of pipes with just random names, which one doesn't really know what they are doing. Most names are cryptic, like all these Mojo things. That's the IPC mechanism that the Chromium sandbox is using, and since MS Edge is Chromium based, they use the same thing. Anything else interesting? Real VNC is apparently also using some pipes to communicate between the service and the component which shows the tray icon. So that would be another application. If you have a service running as a service, then it cannot interact with the graphical desktop. So if you want to have also a tray icon or a window or something that allows you to interact with the service, then you would also need to use two applications, one running as a service and then one running in the current desktop session and communicating somehow. So pipes would be another good communication means for this. I really don't find any more interesting pipes here. As said, most of them are just random names which then internally are generated and used. So for example, here normally when we could check the command line arguments for these functions, you will see that they will have a lot of data that allows them to find the right pipe. So I guess if we look here, okay, this is not part of it. We'll also go maybe for, I mean, it can of course be that they just hash some of the data and then that's how they find the right pipe. Copy cell. Let's see if any portion of the pipe name is present in the command line. Okay, so they have the process ID. That will probably be some thread ID that we don't see here, and the rest. I don't know how they internally generate the pipe name, but the idea usually with these workers is that you start them with some parameter which then specify which pipe they should connect to. But of course you can hash the arguments and do other funny things to them, so it will not be that trivial to find the pipe name if you don't know how internally the program works. Well, but I guess I talked for long enough about those things, since what should have been a break is already over. So now let's create again 2 server applications, but this time for using network pipes, so network sockets. So we create 2 more solutions. Qt console application, that will be TCP server, and the other will be TCP client. Next, finish. The older version of the Qt plugin actually offered you to select the components you want to use while creating the project. The new one unfortunately skips this, so we also always need to add the right components manually. And TCP the other was to server, so this will be client. Zack, finish. Okay, then let's add here the necessary components. Zack, network. Okay, and for the client, this is super trivial. The client will be very short. Just will include TCP server. We don't need those things. Sorry, client of socket. TCP socket. Server we will include in the other one. So is it complaining? That should work. Oh. Yep. Okay, then we will tell it where to connect to. Connect to host. And let's write something. I don't know. Yeah, that's fine. Then let's wait for read. Oops. Wait for read. So this is of course not the nicest way, because we just know that there will be something to read. We don't know how much, but we assume if we send a small enough package that it will be delivered in one go. So we can go with that. Read all. And finally, we want to close the connection. Disconnect from host. Okay, and on the server side we will add again a new class. And okay. And here we can copy most of what we have created for our pipe server. We'll just change a few things. So let's start with the simplest thing. As argument we'll be passing the port on which it will be listening. Okay. Pipe server H. Just copy everything. Just replace pipe with TCP. Okay, what do we need to change properly? So here we need to go for port. Q16 port. This will be Q TCP server. Oops. This okay here will be a socket Q. And here as well. Wait, reader yes. Socket as well. The rest doesn't change. Should be fine. Okay, that should not be pipe reader. That should be. That did not work. Why didn't this work? H pipe TCP. Okay. Strange. Okay, now that worked. So now we also copy the CPP file to our. Oops, that is slightly too large. To our server. We do the same replace. So this will not be correct for all cases, but for most of them. So here we go with QU in 16 port. This will be TCP server. TCP server. Why is it complaining? It should not be complaining. You will see once we are done with all the refactoring. That should be fine. That's the error. We want an unsigned int for the port number. Okay, now Q TCP server, and this will take the. This doesn't take anything for now, but here when we need to listen, we want to specify Q host address any, and then we need to specify the port on which it will be listening. And the rest behaves quite similarly, so this should also have a new connection, and it has, and it will also have a next pending connection. So as you see, they implemented those things all very similarly. We can keep that as called socket, and here TCP reader, TCP socket for the client as well. And that should be all. Let's run it and see if it works. Okay, it needs to compile, then let's quickly start the other one. This might quickly fail if it compiles first, but that's up to chance which one will be first, although I guess server, since we started compiling of this faster, yeah. Okay, yeah, we need to allow network access in the firewall, although for the local host connections, the Windows firewall is not set up to be able to block local host connections, which is, well, I don't know why they did it. It would be nice to be able to block local host connections as well. Let's quickly restart it again. So we start the server. Now this one should be able to receive connections, and now we start this one. Okay, something's not working quite right. Let's start. Create the service. The server is still running. Let's check whether it has a listening socket open. TCP server sockets. Well, it has, it's listening, so the connecting client should be able to connect to it. The port is the right one. You can step. I don't think I installed any third-party firewall. No, I did not. Okay, step. Well, it connects and it sends. But nothing happens on our server side. Let's then debug the server. So we have the server. We start listening on any and the right port. Is it the right port? Yes. Then we should enter here and there, and we should end up once here, and we should end up there. Oh, I know why. Because we are not sending. We are not sending the terminating null. It's waiting forever. Right. Comma. That should actually work with a single character. Or not. Okay, it doesn't want to do that, so let's go with this approach. That will send us the terminating 0 explicitly. The book. Delete all breakpoints. Since I assumed that everything was fine, we just forgot the 0. We don't need that breakpoint either. So this one is running. This one is still waiting for the program to be compiled. Yep, and it's working. So as you see, as you have seen, using a nice high-level framework can save you a lot of work typing things manually in your program. Now I realize, of course, that the very simple pipe server approach we took here looks like it's less code, but really as soon as you would want to have some higher complexity, then that would become even much more code, so it would not be that user-friendly at all. What we can now do, since we have our server running, we can also implement the client not using Qt. What was the header for that? Hash include. We need Windows H, and we need winsock 2 vs. What's that? vs2 winsock 2. Okay, that should be all that we need. VS should be a VSR. There was some initialization function Windows needed. It was called startup, VSR startup. I mean, I'm pretty sure Qt would have done that as soon as we include the element anyways. Okay, it needs some arguments. Requested version, I guess we want version 2. And that I don't remember. Let's see what this thing wants. Okay. This, oops. So the other thing will be a return parameter, and apparently by now there is a version 2.2, so let's go with that. Okay, so now the sockets should be up and running, then we can create a socket. Socket. AF init, that's IPv4 type. What was it? Something TCP. That's the thing for the protocol. Sorry, wait. IF init type. Okay, then I don't remember. I thought that would be protocol. The really nice thing about Qt is that it helps you by providing really easy to use functions, so that you don't need to remember all the APIs and what all the parameters are called. So for example, with Qt they will have for every individual argument they will have a enum with the right type, so that it's not like here that it just takes an integer and you don't really know what to put in there. So here we need to put sock stream, and then apparently as protocol we can go with 0. Okay, then we will need to connect it. This connect. Okay, socket is S, comma. Oh, great, it does not. Sock and in SR. Null. Null, comma, null. I think everything else can be null, and we need to initialize this. There was a function somewhere where we can generate so what was it? We can resolve a hostname and get an IP to it. That will fill out for us most of the structure automatically. Get host by name. Get host by wait. Okay. Then we just go for localhost. Why is it complaining? What did this have? Const char, that should be fine. I did not have a typo here. Okay. And that should not make any difference. What did I mistype here? I don't think I mistyped anything. It's also complaining about. Okay, this needs a reference. That's clear. Const socket address reference name SR should be fine. Let's first go with. Let's quickly check what it is complaining about. If we try to compile it, it will give us a better error message. Build only. Oh, that's the problem. We should comment out all those Qt stuff. It doesn't like that. Is this actually already included in Windows? That could be, of course, also the case. No, it's not. Apparently some part of it is included. Okay, this looks better. Just need to include the right header file. Where was that in defined VSR start? Let's quickly check in the Microsoft documentation which library we need for that. VS2lib. Okay. Okay, so the code was right, just that Windows apparently... So the Windows header includes a huge amount of different headers, and presumably they include the version 1 of WinSock. Hence, this does not play nice with the code that we have here. Okay, so we have our resolved hostname, then we should be able to connect. Sock other in, that should be in my opinion. Why is it complaining? I should just cast it, I guess. Sock. Into our socket address. Is in address. We want to copy it there. 0. Length. Okay, so we have this, and then we need to set the port somewhere and some other things. So s in family is equals f init, and the port is equals okay. That should be it. So now it should probably establish the connection, and then we should be able to send something, to write something to the socket, the same way as we would write something to a file. No. Do we need to include something else? And that should be everything that we need. Always just write socket without VSA. Nope. So we started the thing, and so we created the socket, we connected the socket. Yes. On Windows they don't they have separate functions for socket sending and receiving, so it's not as convenient as in Qt that you can use the same functions for everything. Let's make a equals test 3 and equals from our buffer +1 comma len flag 0. Okay. Then that's that. Then let's close the socket. Comma I'll go with SD both. How to write that correctly? There is another option to both. That's how you write it. Okay. So this is still running, but maybe let's send a different text. Let's run it. And as you see, it's working as it should. So Qt is very convenient, as I mentioned already. Especially that it really gives you a full platform abstraction, so you can use the same code that we've written here. You could compile this on Linux and it would run and work just the same way. So this is very, very nice. What could we else try with sockets or inter-process communication for now? We could try a different socket type. So what we used here is a TCP socket. So it is a streaming protocol. It allows us to send a data stream, and it guarantees that whatever we send will arrive exactly as we send it at the receiver, or the connection will be broken. Alternatives to this would be UDP, stands for User Datagram Protocol, where you are just sending single packages and you have no guarantee whether they arrive and if they even arrive in order. So you could send 3 packages and they could arrive in any order at your receiver. So if you are using UDP, it is up to you to ensure that your communication works, basically. And the UDP, unlike TCP, is not connection oriented, so you don't have a client object in this sense. The only thing you have is just 2 UDP sockets, and then you specify the different ports on which you want them to communicate with each other. So we can create here yet another project. Create new project. And then we will demonstrate this UDP communication, Qt console application. UDP client 1, and we will create another one which will be called UDP client 2, which will pretty much look the exact same, just with just communicating to the other one. So one we have, then we need another one. Create project. Okay. Qt. Wait, did I select normal console application? Shit. I wanted to make a Qt application, so I will need to recreate UDP client 1. This one is being created. Okay, next. Okay, so for this thing we will also create a new object class. It's a UDP CUDP client. Okay, so now here in the header we will include first we need to add networking again. modules networking. And for this one we do the same before we forget it, and then wonder why I did not compile. Bugging, advanced, okay, that was here. Zack, core, modules, network. Okay, so client, need to include QUDP socket, Q object, Q client, Q16 port, comma Q object. Okay. Then let's go and implement it quickly. We will of course need to have here some on datagram. I'm not sure but that will have some arguments here. We will have to check that later. But now let's first create our let's first create our socket. So we don't need a local variable, we can just go with the name directly. QUDP socket, that doesn't take arguments, and now bind to port, and that's the mode is fine, so we don't need to specify anything else. Now we want to see quickly what things this what signals does it have. So apparently not many. It's derived from abstract socket. We connected, and those stuff is not relevant because we don't have connections. Okay, then it will just emit ready read and stuff like that once it is that is boring, but okay. So connect to. Let's go quickly to the was that abstract socket, UDP socket. That's pending datagram, datagram says that received datagram, network datagram. Okay, then there should be an event. There should be a signal that tells us that there is a datagram waiting. It's not here connected. One moment, please. QTC. Okay. I mean, it probably will be just reusing signals that are used for things available to be read. Size read datagram. Yeah, it really reuses just a normal ready read message signal from QIO device, which we this one which we used before already in our other clients, so we will just call this on datagram. Connect ready read, comma, this slot on datagram. Here we can then read it using what was it? Read datagram, and there we have all the things that we want. So that is not the most user-friendly interface, but okay. Buffer host address will be the center that sent us the data, then the port. Okay, and then we can write datagram. Data. Let's go with one of the other ones. We could go with this one. Oops. Reply. Zack. We want to reply it to the sender, so to the person that sent us the first request. Okay. And now we just need to go to main, include our client, and start it. So new UDP client. The nice thing about UDP is that there is no server in that sense. So you only have clients which are just communicating with each other on equal ground, so to say. So let's start this. Then quickly write the other end. Here we can be a bit more short about what we write. We won't use the oh, that one needs to be different. I don't know. 1, 2, 3, 5. Wait, something complained. Right, so we start this, we create this, that should be working. Yep, now it works just fine. Okay, and the other one, so we have this, and then right datagram, and here we will queue things that queue byte array request. You can just put any string and queue host address 2 and port was 1, 2, 3, 4. So the important thing is, of course, that we cannot use the same port for both clients on the same machine. On different machines, of course, we could reuse the same port. But now we'll put a breakpoint here, and when we start this client, it should. We want to read the data. So wait for ready read. Read all. Read all will work, but we should use read datagram. Read datagram. just copy the whole thing. Port sender. Okay, it's fine. Read datagram. And now qdebug. That should work. And done now. So it will. Aha, we forgot to add some printout here. So let's add this as well. Okay, let's restart our server. Put the breakpoint here then. Start our client. The first time it might fail because of the firewall, we will see. Doing something. Okay. Why didn't the break one of the windows is alt? Yep. Okay. So we see that the port is the 1235 from which the other one is sending the data. We have the request, and if we now allow it to continue, the other one will also print it. So it works nicely. You can start this as well again so that we see that. Did I restart the wrong one? No. Client 1. I closed the server. Client 1 was the server, client 2 was the client. Or rather, okay, we don't want the breakpoint. Okay, this one is terminated, so let's restart. That was client 2. Yep, working nicely. Any questions about networking at this point? I went through all the things rather quickly, assuming that there is already some basic knowledge about networks, but if you have questions about TCP or about UDP or about the underlying IP layer, then that would be the time to ask them. No questions?
Yes, maybe you can give a short introduction on the difference between UDP and TCP. I know some network basics, but I'm not quite sure on this.
So TCP is connection oriented and much more sophisticated than UDP. The thing is with TCP, as we have seen in the first example, TCP server, you always have one peer in the network which acts as a server and is waiting for incoming connections. And then you have the client. So when the client wants to start to talk to a server, it will send to it a package, a so-called sync package, with some configuration information, and then the server will send back an acknowledgement package. Then the client will send again an own acknowledgement package. So it's like a three-way handshake, and at this point the connection is established, so the server side will create a new socket object which can then be given to some thread for processing, and the client can start sending data. Of course, the server could also start sending data on his own, so it's not necessarily specified which side starts with the communication. It's just customary that the client is the first one to send a request, and the TCP stack in the operating system is responsible for ensuring that everything that you send through the socket will arrive at the other end. So when you use the send or write functions on a socket and put in data in a certain order, the data is treated as a stream, as a byte stream. So there is no like boundaries internally. So if you have if you put 3 packages on the socket, then it is like just one long piece of data. On the other end, you have no guarantees whether the recipient will know whether 3 packages will arrive or not just one very long package with all the data appended one to the other. And in fact, internally, it is implemented such that the operating system's network stack can select the package size. So it will try with usually about one kilobyte package size, and if it, and it will send the package, and then it will wait for an acknowledgement from the receiving side, and if the acknowledgement package does not arrive within a certain period of time, it will then halve the package size and then just send half of the package and see if it then receives a acknowledgement, and it will repeat that a couple of times. If it never receives an acknowledgement, then it will set the connection as broken, and here in Qt you would get the disconnected slot signal fired. And if it works, so if it manages to connect to send the package and get the acknowledgement back, then it will increase the package size slightly and then send the next part of the data that it has in the buffer until the whole buffer has been transmitted to the other end. And what also of course can happen is that it will send the package, and then at some point it will no longer wait for acknowledgement, but it will send the package and another one and another one, so for example 3 or 4 or 5 packages, without having yet received acknowledgements for any of them. This is called the send window. It specifies how many packages or what length of data in total can be en route at any given point in time. And then once the acknowledgement packages arrive, it will send the next blocks from the buffer, and it will also check with the packages, with the acknowledgement packages it received, whether for example you got like acknowledgement for package 5, 6, 7, not 8 but 9, 10 and 11, and then it sees one is missing, but other acknowledgement packages already arrived, so it will not wait for this one package to time out. It will just normally resend faster this one package, and then the receiving side, which is getting those packages, so is responsible for putting them back together in the right order, and also for buffering data in case some package is missing in the middle. The way it is ensured that the receiving end knows how to reassemble the packages is that the packages are tagged with a sequence number, which denote the position in the stream where the offset is where this package's data start. So you have this way means at your receiver to reassemble the stream in the exact order up to where whatever is the last package that you have received, and this part in the buffer it can then be passed to the user part of your application for processing, and all this happens automatically. You don't need to care about any of it. You just know you have something that works like a pipe. You just put in data on one end and they will come out in the exact same order on the other end, or they will not come out, period. With UDP, everything is much more self-made, so to say. You are just with UDP sending a package, and it will be put by the operating system's network stack on the network and sent out. And if somewhere on the route on its way it's lost, then it's lost, and you don't get any acknowledgement or anything. So it's really very basic, a very basic simple wrapper that allows you to craft your own more complicated communication protocol. So there are a couple of protocols like this where you just use UDP and then create your own streaming protocol on top of that, with their own mechanism to resend lost package, with an own mechanism to reassemble the packages into a stream. You could also implement, of course, a custom mechanism which is not stream based, but still packet based. So you have packages of a given size. You will try to send them, but you would have you would expect an acknowledgement, and you would have a mechanism to resend them a couple of times before you deem the connection lost. So this would be like a very small, simple explanation what is TCP and what is UDP. Those both protocols operate on so at the operating system level, so one layer above the pure transport layer. So you can imagine generally any network system. Let's quickly open a notepad or something like that. Don't I have a notepad? Then let's create an empty file. File. It's an empty text file. So So at the very lowest level of your network, of any network, you will have a physical layer. That's layer 1, which is just the electric properties of your connection. So whether it's Wi-Fi or Ethernet, it's not something that you usually care about. It's something that your network card cares about. And on top of that, you then will have a data link layer. So that will be layer 2. Which will be, for example, a Ethernet frame. So if you use Wi-Fi or Ethernet, both are using Ethernet frames to communicate with each other. Such a Ethernet frame contains the MAC address of the sender, the MAC address of the receiver, and then of course the data, plus sometimes a checksum depending on the implementation. So on top of your link layer, you have the third layer. That's the network layer. This will be, as far as I remember already, the TCP, sorry, the IP or IPv6 layer. So at this level, you can specify communication between individual machines. So in this, at this abstraction layer, this is also the data that are sent normally through the internet. So the Ethernet frame is stripped from the data when your router sends a package out to the open internet. It will just, and your router and everything that's not inside your computer will not care about any higher layers. They will only care about the IP address and where the data is going. And once the data arrive at your at the destination, then the layer 4 comes into play, the transport layer. So this will be TCP or UDP, and at this level, so like here at this, so let's quickly write this down. This is just electrical. Data layer, this will be, for example, an Ethernet frame. Here we will have the IP or IPv6 frame. Which will contain the IP address. So let's maybe make an example. We don't care for the Ethernet frames because that's something very specific to, I mean, it's not something that you would care, I think, normally, since it does not touch the internet. But we can take a look how such a IP frame looks. It will have both IP addresses and a couple of additional flag fields. So I will not write everything down, but there will be a version field and a few other things. Then a total length, which says how long the frame is. Some of the informations will be redundant, so a Ethernet frame would have the length, as far as I remember, as well. And or if you look then up to the UDP, it will again, I think, have the length. What else is relevant? We have some other not relevant data. Then we have some more not relevant. Then we have a field which contains the protocol number. So this will specify whether it is with which higher level of protocol this frame belongs to, and a header checksum. So that if the frame would arrive at your destination broken, then you can detect that something's wrong with it and discard it. And then we have the source IP and the destination IP. And lastly, we have then we have some optional data which we don't care of, and then the actual data, the payload. And the way TCP and the way IP is implemented, is such that these frames could in principle be broken into smaller frames on route. So they will have within this data also a fragment offset somewhere to allow them to be reassembled at the receiver. And then on the TCP or UDP level, this is where your computer starts to care about the deeper semantics on the data. First you will have a source port and a destination port. Then you will have again a checksum. So as said, some things are slightly redundant. And then you will have then specific data. So for UDP that would be already everything. UDP only has the source port, target port, checksum, and I think length. Yes. So let's write down UDP. Just source port and length and checksum. While TCP will have much more information. It will also at the start with a source port and destination port. But then it will have the already mentioned sequence number. It has a field in which you can send the acknowledgement data directly with a reply. So if you have bidirectional communication, you can just use the ACK field for that in your own data packet, so that you don't need to send an extra packet just to acknowledge the receipt of something. Then you have some other parameters which we don't care. Flux and then we have again a checksum. This is somehow like the Ethernet frame probably will also have a checksum. We can later check whether Ethernet has checksums, but it's very likely has. And then we have something that's not relevant, and then we have some optional data which no one uses, and then we have the payload. Okay, so this would be the layer 4, and then in principle, if you want to look on what you are doing, you could then specify a couple more layers here, like fifth layer would be session. So this is something that is already up to your application. It is not part of the network stack of the operating system. For example, if you think of a web browser will open many TCP connections to a website. And if you log in on the website, then even though you will be communicating with the website through multiple connections, it will find a way using cookies normally to identify that this interaction it receives belongs to one communication session. So that would be session, and then I would say this is everything that we really care about. Since everything higher up is really, as said, already up to the software developer to develop in detail. Let me quickly just check what data are in the Ethernet frame. Frame. Yep. So in Ethernet frame, slightly different. It starts with the destination MAC address, and it has the source MAC address. Then it has some type field. Then it has the data, and then the checksum is at the end. So there are multiple levels of error correction, and if you usually would then as said, Ethernet has one. Then you have here at the IP level already a checksum to check whether the package is intact that you are sending. Although I think this checksum only applies to the header, it will not go over the payload as such. Then at the transport layer in UDP and or TCP, you also have checksums for every package to verify its integrity. And if you want, you can on higher layers as well implement some additional integrity verification mechanisms. Any more questions? No questions? Well, we are 9 minutes over time, so I think it's a good moment in time to stop.
Could you keep this schema you made in the project file so I can take another look? Yes.
Sure.
Thank you.
Where do I put it?
Because I think it's a nice overlook.
I agree.
Okay, well, it's okay. So just to make it complete, let's just add the additional, at least names for the additional layers that when you specify things you can specify. 7 and 6 and layer 8 is the person sitting in front of the computer. Or smartphone nowadays. Okay, so see you next week. Bye bye.
Thanks.
Thank you. Bye.
Bye.